Hey, Mr. C here. So we're going to do a little motion graph review. So in this video, we're going to review the basic motion graphs and the concepts of slope and area and how they pertain to the motion graphs. We're going to draw some motion graphs for when we have the case of Fnet. That means the net force equaling 0. And then we're also going to draw motion graphs for when we have an applied force, i.e. when Fnet is not equal to 0, when Fnet equals some number. So to start off, let's start off with what slopes mean in terms of motion graphs. So what I'm going to do is I'm going to start off with a basic displacement versus time graph. So what I'm going to do is I'm just going to draw a line representing this. So the first thing we want to think about is, what does this mean? It means as time goes on, my displacement is increasing. Well, for my displacement to increase, I must have what? Yeah, a velocity, exactly. So what we need to do is we need to figure out how displacement versus time relates to velocity. Well, we remember from our reference tables that velocity equals the change in displacement divided by the change in time, which if we use the deltas, it's our final displacement minus our initial position divided by the time it takes us. That looks an awful lot like a slope formula, doesn't it? Well, there's a reason why. Because the slope of the displacement versus time graph, i.e. how fast it's changing, corresponds to the velocity versus time graph. And it's clear because this displacement versus time graph is a linear graph, the slope is constant. So what that means is we have a constant velocity. So going to our velocity versus time graph, if we have a constant velocity, that's like saying we have a velocity of 5 meters per second, or 3 meters per second, or negative 5 meters per second. But it's not a velocity that's changing. So if I want to graph a constant function, if this is my 0 right here, I could have all kinds of things. I could have a straight line going like this. Maybe this would be 5 meters per second. Or maybe I could have a line like going like this. This would maybe be negative 3 meters per second. Obviously, an answer that corresponds to this graph better would be the 5, because it's a positive velocity, and we see from our displacement versus time that it is a positive displacement. All right, well, now let's go analyze our acceleration versus time graph. What you'll also remember from your reference tables is the acceleration is the change in velocity with respect to time, so that's our v final minus v initial divided by the time it takes. And again, take a look at this. It looks an awful lot like the slope. Therefore, it leads me to believe that the acceleration versus time graph can be obtained by taking the slope of the velocity versus time graph. Well, let's take a look at this graph, the velocity versus time graph. If we look at the slope, or the rate of change of a straight line, it's pretty clear that it's not changing. So for this particular graph, the acceleration is 0. If, for example, though, I had a velocity versus time graph, which I'm now going to draw on here. Let's say I'll do it in a different color. Let's say I have a velocity that's changing. I would take the slope of that graph and see that, for example, for this case, it's a constant linear function. That would correspond to an acceleration that has a constant value, like so. All right, well, that's it for slopes. Let's talk about the area. So the only area we're really concerned about right now is the area under the velocity versus time curve. So if I'm going to draw a generic velocity versus time, I'm going to draw a person walking at constant velocity away. So constant velocity, positive, it's increasing. Then I'm going to draw, he maintains his constant velocity for a little bit. And then he begins to decelerate and slow down and go backwards. So what I want to do is I want to analyze maybe what his total displacement was in that entire time. Well, the area under the velocity versus time curve equals the total displacement. So what I can do is I can find the area under this shape. Being a trapezoid, I can find the area of the trapezoid, and I could do that by breaking it up into little pieces and finding all the areas. So if I could find this area, and then this area, which would be pretty easy to do. And by doing so, if I found all the area under the curve, I would find the total displacement. So It's really important to know, again, the area under the velocity versus time curve represents the total displacement. All right, well, now let's move on to our Newton's laws and how it pertains to graphs. So, we're going to first start off with a case where Fnet, the applied force, or the sum of all the forces, equals 0. Since Fnet, by Newton's second law, equals ma, if Fnet is 0, that means m times a is 0. Well, we're not going to have a mass of 0, so what that means is the acceleration must be 0. So what I'm going to do now is I'm going to start with my acceleration versus time curves, and I'm going to go backwards, drawing what the curves should look like if my acceleration is 0. Well, the a versus t is easy. That just represents a 0 acceleration. There we are, constant 0 acceleration. Now, what we have to remember from class is if an acceleration is 0, that means the object's in what's called translational equilibrium. And that can correspond to two different things. One, person's not moving. Or two, a person is moving, but with constant velocity. So we have two possible velocity versus time curves that would correspond to Fnet equaling 0. The first one is a person not moving, so that would look simply with a 0 velocity. And the second one is a person moving with constant velocity, so that would correspond to a constant function. So it could be a constant positive velocity, or it could be a constant negative velocity. Either would work. Now for our displacement versus time, again, we're going to go back to the two cases again. So the first case, not moving, for a displacement versus time, again, just very simple case. And for the second case, for a person moving with constant velocity, well, remember from the graphs we just looked at, if you're moving with constant velocity, it means your displacement is changing at a constant rate. All these constants should make you think, hey, that must be a linear function. And it is. So this would be constant velocity away, and this would be a line that would represent constant velocity in the negative direction. Great. So that's Fnet equals 0. Now what we're going to do finally is do when the applied force is not equal 0. So this is kind of like our F equals ma lab with the wagon. So in that case, I was pulling with an applied force, so Fnet was not equaling 0. And what we found was when Fnet isn't 0, when it's some number, it means acceleration is not equal to 0, meaning there is an acceleration. So again, what I'm going to do is I'm going to start off with my acceleration versus time and work our way back. So if our acceleration is not 0, it can be anything. For mostly in this class, we're going to deal with constant acceleration, so it would be lines such as a constant positive acceleration or a constant negative acceleration. We could also have the occasion where the acceleration is changing. So things like maybe a graph like this, where the acceleration is increasing. But for the sake of it, let's just stick with a constant positive or negative acceleration. So if we have a constant acceleration, that means what? Acceleration, again, is defined by the change in velocity divided by the change in time. So if we have an acceleration, it means that the velocity must be changing. Therefore, we need to draw a velocity versus time graph, which is changing, again, at a constant rate. All these constants should make you think, again, it must be a linear graph. So we could have a constant positive acceleration. That would correspond to this one. Or we could have a constant negative acceleration, which that would correspond to this one. Okay, now we're going to do our displacement versus time. And again, what you guys should remember is we should be thinking about our ball toss lab and everything we've done so far. If we have a changing velocity, it means our displacement is changing at a non-constant rate. It means it's going to get bigger and bigger if your velocity is increasing, or smaller and smaller if your velocity is decreasing. So what that represents is, and how we draw displacement versus time, is by drawing a parabola. So, for example, right there, that would represent a constant positive acceleration, or we could have a displacement versus time graph which is decreasing, like so, and that would represent a constant negative acceleration. Looking at the red graph also, that kind of makes you think about like a path of a ball being thrown, doesn't it? Like maybe off the top of a cliff. Like if this was a cliff right here and a person threw a ball. So if we have a constant negative acceleration right here, that would correspond to a graph like this. And that makes sense because what is the acceleration going on when we have a ball being thrown off a cliff? gravity. So so all the graphs make sense and correspond to one another. All right, well, I hope this helped. So when we get graphs and we're asked to find what the graph would look like when Fnet equals 0 and Fnet doesn't equal 0, go back to this and try to work your way through it. All right, thanks a lot.